Welcome to our next lecture on compiler construction. After we've taken a quick look at how parsing works in general, we'll take a look at how top-down parsing works in detail, and in the second part of the lecture we'll take a look at how to automatically construct a parser that is working as an LL1 parser. So first we'll quickly revisit the problem of ambiguity of grammars, and then we'll show a method to eliminate left recursion. And finally, based on this, we'll talk about top-down parsing using first recursive descent parsers, and we'll take a look at their structure and how to implement them in C code. And then we'll take a look at table-driven LL1 parsers and how to automatically generate these tables. So you've probably seen these slides in our previous lecture already. So we've talked about one big problem when designing grammars, and this is the ambiguity of grammars. So for a compiler, it's important that each sentence in the language defined by a context-free grammar, and that was all the grammars we've talked about so far. So each sentence in a language defined by a context-free grammar needs to have a unique derivation, and this derivation can be unique rightmost or a unique leftmost derivation, and we've already seen both should lead to the same syntax tree. So a grammar in which multiple rightmost or leftmost derivations exist for a sentence, that's what we call an ambiguous grammar, because it can produce multiple derivations and multiple different parse trees for the same input. And that's of course nothing what we would want to achieve here. So because multiple parse trees, having multiple parse trees implies that a single program you enter can have multiple possible meanings. And this is of course dangerous because the programmer has no way to influence the meaning or needs to remember what things mean. And we've seen an example for this already, this typical dangling else problem. So if we have an if statement, one of these has an else statement. The question is this else statement here related to the inner if, or is this else statement instead related to our outer if statement? So if we use this very simple grammar here, so from a statement we derive a terminal symbol if, a non-terminal symbol expression, terminal symbol then, non-terminal statement, terminal else, and non-terminal another statement, or if expression then statement. Our compiler has a problem to decide, does this else belong to the current if expression it's looking at now, or to maybe another one that came before this. So if we are trying to run our example through this grammar, it really depends on if our grammar or our parser chose the first rule first or the second rule first, and then we have two different distinct rightmost derivations with different behavior. So in the one case here, the else belongs to the inner statement, and in the other case, the else belongs to our outer if statement. And of course, depending on how you write your program, this can have very different outcomes. So we've already seen a method to remove ambiguity from a grammar. So we can modify the grammar to include a rule that determines which if controls an else. So now we have a statement, and this statement is extended now with a with else statement. So we've replaced the statement, which would just recursively go up here, with this with else new rule we've introduced here. And this with else rule then includes the else statement. So this makes it unambiguous. The solution restricts the set of statements that can occur in the then part of an if then else construct. It accepts the same set of sentences as our original grammar from before, but now it ensures that each else has an unambiguous match to one specific if. So let's take a look at another example for our grammar here. So here we know we only have one rightmost derivation for the example, and then we can go through this. So we start with a statement, so our start symbol is the first non-terminal symbol here in our grammar, and then we go to if expression then statement, and then we can extend this statement by actually going to this one here, and then we know we have a with else somewhere, otherwise we'd have no with else. So essentially we expand this to expression then, if expression then with else statement. Then we can from the right hand side replace a statement by assignment, and then we can replace this again by another assignment here, and then we're done and we have an unambiguous resolution, so we actually know which if statement this else statement belongs to. So we've already seen that the order of derivations in an unambiguous grammar actually shouldn't have any influence on the outcome of the parse tree, so on the structure of a parse tree. And so we've seen for this example grammar already here that no matter if we start from the right or from the left to resolve all the non-terminal symbols, actually we end up at our same identical parse tree. So here in our rightmost derivation we would first have our expression as our start symbol, and then, well, we start replacing expression from the right, which is easy, and then we replace this by expression of name. Then we can replace the operand, and then finally we can replace the leftmost part by replacing the expression by what is inside of our brackets here. Inside of our brackets we can have another expression with an operand, and then we replace it from right to left again until we only have terminal symbols in our syntactic form here. And if you start from the left hand side, it works out all the same. So first you would expand the brackets here, then you would expand the expression inside the brackets here, and then you would start expanding from left to right, so name, then the operator, and in the final step you would then apply the final rule by adding the operator and putting the name at the end. And the parse tree that comes out of this is actually identical for both derivations. So it looks like this. Of course, on top we have some sort of multiplication operator and a name, and then it follows our hierarchy, which we try to introduce using our brackets here. So it works for both, and it gives an unambiguous resolution for this grammar here. So one problem that's showing up when you design grammars is that parsers don't have unlimited what we call look ahead. So look ahead just means we can take a peek at the next token essentially that is delivered by the scanner, so that if we only could take a look at one single token, that would be a look ahead of 1. If we could have a look at 2 tokens, a look ahead of 2, and so on. But in any case, parsers and scanners only have a limited look ahead to upcoming tokens. So if we have a production like this here in our grammar, so our non-terminal symbol A resolves to A, B, C, D, E, F, then a non-terminal X, and then GH, or A, B, C, D, E, F, and then something non-terminal Y, and then again GH, then the parser needs to read all the first 6 characters here until it can decide, well, can I go to X or can I go to Y? So if our parser only has one character look ahead from the scanner, it's unable to choose between the 2 productions. Now, there's a way to resolve this problem, and this is pretty easy. So we're looking at common prefixes, and that's very similar. The idea behind this is very similar to our conversion from NFAs to DFAs. So what we do is we try to postpone the decision which of the rules to take until it really makes a difference. So what we can do is we can rewrite this production here to A is resolved to A, B, C, D, E, F, and then something we call A prime. And A prime then can have either a resolution to non-terminal symbol X and GH or non-terminal symbol Y and GH. So this preserves the language, so it's the identical language that's recognized here. Of course, we didn't say anything about X and Y. And by just adding this one production to go from A to A prime here, which essentially encapsulates this difference, whereas the beginning then would always mean we're in state A, and then we'll have to decide whenever we've read these first 6 characters, and only then which of the rules to take. Whereas here we would have to decide earlier because these are complete rules. This preserves our language, and this helps us, this common prefix, to make our parsing easier. Another problem that commonly shows up when we define grammars is so-called left recursion. So let's take a look at a very simple grammar here that just generates a list of A's. So from non-terminal A, we can derive non-terminal A and terminal character A, or simply a simple terminal symbol character A. And then we can derive the following words. So we can immediately, as the first rule, apply the second reproduction here. So we can just produce a single A. There's no more non-terminal symbols, so we're finished. Or we can take the first production here first. So we can go from A to AA, and then resolve the A recursively here by then taking our second production. So this would produce 2 A's, and so on and so forth. So 3 A's, and so on. Now, our production here that we've used, A, non-terminal symbol A, derives non-terminal symbol A and terminal symbol A, is left recursive. That means that our non-terminal symbol, so our head, always appears on the left side of the production. And this would be as we would normally write it. But this is problematic for our parser, because then it would somehow have to parse until the very end, until it can resolve all the stuff, until it read to the end of the text, until it can actually figure out which of the rules to take. Now the same sequence can be generated by this grammar here. So we have 2 rules now. So we resolve non-terminal symbol A and derive from this. Now first a terminal symbol A, and after this a non-terminal symbol, a different one, which is called A prime. And then A prime resolves to a terminal symbol A, or recursively A prime again. So we have the terminal symbol always on the left hand side. And now to finish all this recursion, we need to add something. And this is our second rule for A prime. So our second rule for A prime means that A prime can also resolve to epsilon. And epsilon is the empty string. So the empty string that returns from the production. So we see now we derive our words consisting of multiple A's from the other side, so from the left hand side. So we can start, applying which rules? Let's see for that one here. So non-terminal symbol A derives a single terminal symbol A as a string. So we'd have to go through this grammar, say, okay, non-terminal symbol A derives a terminal symbol A and A prime. So we have our A already produced. We need to go to A prime to resolve the rest. And there's no more input. So essentially A prime directly goes to epsilon, so the empty word, and we're finished because epsilon is a terminal symbol. Or we can take this a bit further. So we can go from, A to A prime again. That's what we always have to do. And then we can go once through this recursion here. So we have one A here, another A here. And in the second iteration, we chose the production that generates an epsilon for A prime. And we can go through this recursion as many times as we want until we end up resolving A prime to an epsilon. So we've seen for this very special example that it's possible to get rid of this left recursion. And the question we need to ask ourselves is it actually possible in a general case to eliminate this left recursion, which causes lots of problems for our parsers? So let's take a look at a more complex definition here. So we have to get a bit more formal. So if we have a non-terminal that has m different productions that are left recursive and n other productions that are not left recursive, we can write it like this. So in this rules here, we have Greek letters introduced like alphas and betas. So the Greek letters here stand for some arbitrary combinations of other terminal and non-terminal symbols, with the exception, of course, of the epsilon, which we already introduced as the terminal symbol standing for the empty string. So we have some left recursive productions here for A, so A derives, A alpha 1 or another alpha 2 and so on. So this means we always have a recursive A at the beginning and then just some other combinations of terminal and non-terminal symbols after this initial non-terminal symbol A. And we can have some other productions for A that derive to something else, which has something else than a non-terminal symbol A at the beginning. We just call them beta 1 to beta n. Now we can use the same trick as before, so we can introduce A prime, and then we can start to rewrite our productions. And this has already been investigated quite a number of years ago, so here's a literature reference if you want to dig deeper. So we can replace these rules by resolving A to beta 1 A prime or beta 2 A prime. So we take all of our betas here first and only have one production for our non-terminal symbol A again. And then we can have our non-terminal symbol A prime, which we introduced here, and then can put all the other repetitions of A prime behind it. So we take the alpha 1, the alpha 2 until alpha m A prime. And we've already seen this in our previous example. We need to add the epsilon to finish this recursion. So you can try to check with our previous very simple example that this previous very simple example is exactly a very simple way of applying this technique. And when we apply this technique to eliminate left recursion, then this generates the same language, and it has the benefit of removing this immediate left recursion. Now, what's an immediate left recursion? An immediate left recursion means that, well, we recurse from our non-terminal symbol directly again to our non-terminal symbol on the left-hand side. There can also be some indirect left recursions here. For example, if we have productions like this, we go from non-terminal symbol A and resolve non-terminal symbol B and an X, and then from B we can go to non-terminal symbol A and a Y. So we have this chain of derivations here from A to BX to AYX, and this of course again has an A on the left hand side when we derive it from an A. So what can we do with all that we've learned so far? So we've seen context-free grammars so far, and we've seen how to derive these. We've seen how to construct syntax trees for context-free grammars. We've seen problems of ambiguous grammars, and we've mentioned there is no single true way to disambiguate them. It depends on what we want them to stand for, but there are ways to disambiguate them. You have to decide for one or the other option you can choose. We've seen left factoring. This always shortens the distance to the next non-terminal. We can see that we can eliminate left recursion, and eliminating left recursion always shifts a non-terminal to the right, which makes our grammar easier to build and our parser easier to write.